Most of the calculus that we are going to use from here on through the rest of the semester is going to involve the three-dimensional coordinate system. In a lot of ways, Calculus 3 just re-examines a lot of the concepts that we learned in Calculus 1, except we take those Calculus 1 concepts and adjust them a little bit just so they can work in the three-dimensional coordinate system. So we're going to be seeing a lot of three-dimensional graphs. And typically in the XY plane, we would see the X and Y coordinate as the horizontal and the vertical. But when we're in 3 dimensions, we're going to label these a bit differently. The horizontal and vertical components, imagine them being flat on your screen. Those are actually the Y and the Z axes. And this slanted line that I drew, we actually want to try to imagine that line coming out at us in a 3rd dimension, and that is the x-axis. When it's coming towards us, it's the positive x, and when it's going back, it's negative x. When we go to the right, that's positive y, and left is negative y. Up is positive z, and down is negative z. These 3 axes separate the space into 8 octants. The first octant is the only octant that we ever usually call by name and really has a label, and that's the octant where all of the variables, all of our coordinates are positive. So it's forward, right, and up. So imagine this little cube on the front right-hand side of your screen, the one that's above the XY plane. That is the first octant, and that gets referenced quite a bit. We are using something called the right-handed system. And what this means is if you imagine yourself standing here at the origin, looking into the first octant, so you're looking this direction, and this direction. The x-axis is going to be the axis on your right. So if you imagine my little stick figure here, his right hand is in the same direction as the x-axis over here on the right. And that's what makes this a right-handed system. If we were to switch the x and y axes, then it would be a left-handed system. But everything we're going to do this semester, we're going to have our 3 axes set up as a right-handed system. To plot points in the 3-dimensional system, all of these axes are at 90-degree angles, but the way that we have to visualize 3 dimensions on a 2-dimensional screen here is with that diagonal x-axis. The xy plane in these 3 dimensions is the plane that's completely horizontal. And if you look, that angle right there doesn't look like it's 90, but it really is. So when you locate a point, you have to use parallelograms that match the angles that these axes are drawn at. It's really not difficult once you do it a couple of times, but just to think about it, I guess at first might seem kind of strange. So we're going to plot a couple of points really quick just to get the hang of it. So I'm going to draw a new set of axes. So x comes out at us, y goes to the right, and z is up. And we're going to plot the point 2, -4, 3. The very first thing that you should do is you should draw a parallelogram in order to find where we are in the XY plane. because those are the two that don't look like they're making a 90-degree angle. And in order to get this point accurate, we need to make sure that when we travel on the x-axis, we're traveling parallel to the y-axis. And when we travel on the y-axis, we're traveling parallel to the x-axis. So we need to locate the point, or the value 2 on the x-axis, and the value -4 on the y-axis, which means we're going to move to the left. And we need to make a parallelogram that uses these two sides, and we're going to finish out that parallelogram. So I'm going to do some dotted lines here to roughly show you where we're going. So that is approximately the point 2, -4 in the xy plane. And it's not straight out from 4 or straight out from -2. We've got this parallelogram because visually, when we look at 3 dimensions on a 2-dimensional screen, we don't actually see that 90-degree angle right there. It looks less. So this is 2, -4, 0, because I have not moved up or down yet any. Once we know where we are in the xy plane, we can then move either up or down based on our z-coordinate. So we want to move up 3 units. And this can also be tricky because I'm not going to take this all the way up to where it looks like 3 is on the z-axis, because right now it actually looks like we're at a value of -2 on the z. And that's just an illusion, again, based on looking at this 3D space on a 2-dimensional screen. So a distance of 3 units is this long. So I need to take that length and transfer it over to where I have plotted my point on the xy plane. And I want it to be about 3 units long, based on however we decided to draw our tick marks on the z-axis. So those two lengths are about the same. So that is approximately 3 units on the z-axis. So this point right here would be 2, -4, 3. Again, we first do a parallelogram in the xy plane, and then from there we can go up or down based on our z-coordinate. Many of the formulas that we introduced in the last section, we can very easily extend to 3 dimensions. One of the things we did in the last section was we talked about distance, or for a vector, it would be magnitude and sometimes called norm. So now we could have vectors that have 3 components in them. They could have an x component, a y component, and a z component. Now, because I'm writing this in component form, that means I'm referring to a standard position vector. Remember, standard position vectors start at the origin, and then they go to the point represented by those components. The magnitude of a 3-dimensional vector is the distance formula again. The Pythagorean theorem we could use, we'd have to do it twice. But just for the sake of simplicity here, remember the length of a vector is the distance from the start to the end, from the initial to the terminal. So if it's in standard position, the initial is 0, 0, 0. And if you apply the distance formula out to your v1, v2, v3 point, we're going to end up with just v1 squared plus v2 squared plus v3 squared. So all I did to transform my 2-dimensional magnitude into 3-dimensional magnitude is the inclusion of this new third component. And we combine it with our other 2 components the same way that the other 2 components are originally combined in the formula. They're squared and added together, so I do the exact same thing for V3. I square it and add it in with my other guys. And we'll do a comprehensive example that uses several of these concepts in just a minute. We didn't talk about midpoint in the last section, but you've probably learned an algebra midpoint formula before. And this is just for the sake of looking to see what it's like in 3 dimensions. So if we have 2 points in three-dimensional space. So I'm going to distinguish them with those little subscripts. Point 1 has subscripts of 1, point 2 has subscripts of 2. The way I can find the point that is exactly halfway between them is just using the concept of average. So this answer is a point in three-dimensional space, so it will have 3 coordinates. So I want to find what x value is exactly halfway in between x1 and x2. And the way that you do that is just add them together and divide by 2. And we do the exact same thing for all of them. Now I want to find the point that's exactly halfway in between y1 and y2. So I add them together and divide by 2. And the same exact thing for the z's. That is how we find a midpoint in three-dimensional space. The very first surface that we're going to talk about in three-dimensional space are spheres. The formula for a sphere that has a center at x1, y1, z1, and a radius of r is x minus x1 squared plus y minus y1 squared plus z minus z1 squared equals r squared. If you remember your formula for a circle from algebra class, it looks very, very similar. The only difference now is my inclusion of what exactly is happening in the z direction. And I follow the same exact pattern that I see that's happening to my x's and my y's. The x, y, z that we see at the start of the subtraction, those are variables. When we write the equation for a surface or even just a two-dimensional graph, we always have variables in the equation representing the fact that there are a lot of different points that satisfy this equation. And the graph is just all of those points plotted and connected. So those first x, y, and z's that we see in the parentheses, those are variables, and they will stay as letters when we write out the equation. But the x1, y1, z1, those values come from our center. And then the r is the radius. So we're going to try to tie all 3 of these together with one example. And there are several different ways to do this. So when you first look at this example, if you were thinking of a different way to do it, that's perfectly fine, but you should get the same exact final answer. So what we're asked to do is find the equation of the sphere that has a diameter with endpoints 0, 2, -4, and 6, -4, 0. So a sphere, if you slice it through the center, no matter what direction you slice it in, you should always have a circle. So vertically, I've got a circle. Horizontally, I have a vertical. And then this little sideways slice is also a circle. And what we have is 2 points on our diameter, which means they are directly across from each other with the center of our circle being exactly in the middle. So 0, 2, -4, I'm just going to randomly plot these. I'm going to say is right here. And then 6, 4, 0, I'm going to say these are here. Now, if you draw axes, you'll see that these points are not accurate, but just for the sake of understanding exactly how we're going to find the information we need, I wanted to have a visual. So a good technique for problem solving is always first read the problem, but then identify what your ultimate goal is. And in this problem, the ultimate goal is to find the equation of a sphere. So I'm going to refer back to the equation of a sphere. And the way that we've defined it, we need to know the center and the radius. And neither one of those were given to us. But if we can find the center of the radius, then we can write out our final answer. So that's where these diameter points come in. You might also remember that exactly halfway in from the diameter is the center. So the center is technically the midpoint between those 2 points. So we can find the center just by doing the midpoint formula. So our center is going to be at the average of all of those coordinates. So the average of my x coordinates, the average of my y coordinates, and then the average of my z coordinates, which is going to put us at 3, -1, -2. So we've got half of the information that we need in order to write the equation for this sphere. The other piece of information we need is the radius. So you need to remember what exactly the radius is. The radius is the distance from the center out to the edge of the circle. And what's unique about a circle is that no matter what edge point you go to, it should always be the same distance. So what I'm going to do is I'm going to use one of the edge points that I already know. I'm going to calculate the distance from the center that we just found out to either one of the edge points. It should not matter which edge point you use, you should get the same answer. So I'm going to use our distance formula and the point 0 to -4 and figure out what that distance is. And that distance is my radius. So the radius is going to be, and this is just a 3-dimensional distance formula we talked about earlier. We do the difference in the x coordinates and square it. So I'm going from the center out to the edge, plus the difference in my y coordinates squared, and the difference in my z coordinates squared. And some quick little calculations, and we get 3 squared, which is 9, -3 squared, which is again 9, and then here -2 minus a -4 simplifies to -2 plus 4, which has a final result of just +2, and that value squared is 4. So we get the square root of 22. We are not going to change that to a decimal. We're going to leave it exact. Pretty much everything we do this semester, unless we are explicitly told we can use decimals or approximations, we want to leave it exact. So we have now found all the information that we need in order to write the equation of this sphere. We've got a center at 3, -1, -2, and we've got a radius of square root 22. So now we refer back to our equation for a sphere. And the sphere is going to be x minus your x coordinate, which is 3, squared, plus y minus your y coordinate, which was -1, squared, plus z minus your z coordinate squared equals your radius squared. And we're going to clean it up just a little bit. You don't need to FOIL these out. We want to keep this in just like standard graphing form because it's easier to see what the center and the radius are, and it's easier to graph it when we explicitly know those values. What we can do though, just to clean this up a little bit, we've got minus a negative. We can change those to pluses, and I've got a square root squared, which those two will cancel each other out. So our final answer, the equation for this sphere, is x minus 3 squared plus y plus 1 squared plus z plus 2 squared equals 22.